Oh, yeah. Hi. Hey, y'all. I guess it's time to do a quick review of Newton's third law. I guess I'm kind of an example of Newton's first right now, though. An object at rest is going to want to stay at rest. But an object in motion is going to want to stay in motion. So let's get moving. We got 3 laws that we need to review on, and I'm going to do all 3 of them in 5 minutes or less because y'all have a test to get ready for. Are you ready? Newton's first. An object at rest stays at rest. An object in motion stays in motion. And it's going to keep going until a force acts upon it to change its trajectory, to change the way it's moving. All right? That one's pretty easy. If I throw a pencil or a pen, it's going to keep on going until it hits that wall. Or until, of course, gravity works on it to bring it to rest. Remember, inertia is anything that's going to want to keep doing what it's doing. It's the tendency for an object to keep doing what it's doing. It's all about the law of inertia. Now, the second law of motion is Newton's mathematical law. It's a law that gets a little confusing sometimes, but I'm going to run through it real quick. And we're going to keep it super, super simple. And it goes like this. Force equals mass times acceleration. Mass times acceleration. The only thing you really have to worry about keeping it all straight in your head is that mass is always in kilograms. In order for our force to be able to be appropriately measured in newtons, our mass has to be in kilograms. And our acceleration, multiplied, right? Our acceleration must be in meters per second squared. Meters per second per second. All right? Now, as long as the mathematic equations that we're working with fit here, you're golden. It gets a little tricky if it says like, let's say a bug is flying along and it has a mass of 0.0001 kilograms. We could do that. But if it says it's 1 gram, how am I going to do that? Don't worry too much. For the test tomorrow, we'll keep it easy. All right? We're going to go with kilograms first. So how do we solve for our newtons? Well, our kilograms, let's say a bug is 0.05 kilograms. And let's say it's flying at an acceleration of, let's say, 4 meters per second squared. Now that looks super, super confusing, and it's totally not. You're just going to take 0.05 and multiply it by 4. So you're going to go 0.05 times 4 equals, move the decimal point, 0.2. Now, you can watch that a whole bunch of times if you'd like to, but all you have to do is remember, you're just multiplying your kilograms times your meters per second. That's your newtons. So how many newtons is this? 0.2. 0.2. Make sense? And we'll talk more about this tomorrow. So Newton's third kind of goes like this. Y'all had a graphic organizer. Some of you did an amazing job. Other of you, I can see how your thoughts are working. So let's go ahead and fill this out really quickly. All of us together, because you can use this on your test too. Newton's third law of motion states for every action, there's an equal and opposite reaction. Which means, let's think about that bug for a second. If it hits that windshield at, let's say, 0.2 newtons or whatever, that force, 0.2 newtons, that windshield is hitting that bug back at that same amount of force, even though that car is a whole lot bigger. Forces are always acting in pairs. They can only act on objects or things that contain mass. So in other words, Newton's laws don't work on things like light or sound. You're just looking at that thing that has mass, all right? Now, things that can get a little confusing with this one right here is, let's say that bug. How is he flying? If his wings push down, what's pushing him up? Think about that for a second. Hint, hint, might be a test question. All right, so all of Newton's third law is talking about newtons and force. So how are they measured? Well, they're measured in newtons. And they're measured with something called a force meter. force meter. We can also use spring scales, but the main thing I want you to remember right here is newtons. Now, it can be direct contact or at a distance. So direct contact are things that are actually touching each other. Me and the wall, a car and a car, a bug and a windshield. All of those go right here with direct contact. At a distance, well, this could be things like the moon and the earth, or a baseball and a bat. Once they're moving in those separate directions, they're no longer in contact, but they're still reacting with that force. Make sense so far? All right, that's where we're gonna wrap up today. So if you have any questions, make sure you can reach out to me anytime and we will get back. I will see you soon. I'm super excited to see how much you've learned. So thanks for joining me. Bye.